For any help regarding mechanical assignment help, visit https://solidworksassignmenthelp.com, email info@solidworksassignmenthelp.com, or call us at +1 678 648 4277 solidworksassignmenthelp.com. Problems and solutions. Instrumented nanoindentation is a new technique in materials science and engineering to determine material properties at very fine scales. A typical indentation test is composed of a loading and an unloading part. The loading part is used to extract strength properties. The unloading portion is used to extract the elasticity properties of the indented material. We have already studied the link between strength properties and hardness measurements for a flat indenter, homework set number 2, and for a conical indenter, quiz number 1. This exercise deals with the link between elastic properties and the indentation result upon unloading. An indentation test is a surface test, but its effect is felt in a bulk volume of characteristic size L around the indentation cone. Within this bulk zone, the material undergoes deformation as a consequence of the indentation, while the material situated outside this zone will not feel the localized indentation, no deformation. The focus of this exercise is to estimate this characteristic size L associated with the elastic unloading by means of the upper bound displacement approach. To this end, we consider a rigid conical indenter of half apex angle alpha, which, during the loading phase, has penetrated into the material to an indentation depth h, see Figure 1 top. At this stage, we consider infinitesimal unloading, sh. The slope of the unloading, df/ds0, see Figure 1 bottom, is related to the stiffness properties of the indented material by SolidWorksAssignmentHelp.com, where A equals pi r2 is the projected contact area at the surface z equals 0, see figure, and m is the indentation modulus. In this exercise, we will first establish an upper bound for the relation between m and the elasticity constants of a homogeneous, linear elastic isotropic material, characterized by the Lamé constants lambda, g, equals const. Then, we will use this solution to evaluate the characteristic length scale L. Throughout this exercise, we will assume quasi-static conditions, inertia effects neglected, and we will neglect body forces. 1. Kinematically admissible displacement field. For purpose of analysis, we consider two subdomains of finite size, noted respectively 1 equals pi r2L and 2 equals pi r2L, 1 plus L/r, minus 1, see Figure 1. Both domains are assumed to extend by a length L in both the vertical and the horizontal direction. The displacement is assumed to be non-zero only within 1 and 2. The displacement in the rest of the half-space, i.e., situated outside omega equals 1, 2, is assumed to be 0. In 1 and 2, we consider vertical displacement fields of the form A for both domains, 1 and 2, and their common interface, specify the conditions which function phi z, r, I equals 1, 2, need to satisfy so that psi is kinematically admissible. Hint, the indenter is a rigid cone, and the test is displacement-driven. B. We consider a linear form of the displacement in 1 and 2, that is, SolidWorksAssignmentHelp.com. Sketch this displacement field in Figure 1, and show that it is kinematically admissible in omega equals 1, 2. C. Determine the non-zero strain components in 1 and 2. Hint, go back to the geometrical interpretation of the linear strain components. By means of very precise mechanics argument, show that the displacement field psi is not the linear elastic solution, psi sigma, of the problem. 2. Potential energy. We will employ the upper bound energy method, T psi, less than or equal to T psi, notation as in lecture notes. A. For the displacement-driven indentation test, show that the potential energy of the solution of the problem reads epit psi equals 1 df s2 2 ds. Display this result in the T-curve in Figure 1, bottom. B. Using the displacement field psi defined by 3 and 4, show that the upper bound of the potential energy epit psi reads SolidWorksAssignmentHelp.com. C. With the results of 2a and 2b. Develop an upper bound m plus for the indentation modulus. D. Finally, the exact solution for the indentation softness is m equals e slash 1 minus nu 2. From the previous results, determine an upper bound for the characteristic length scale L slash R of the indentation test and determine L slash R for alpha equals pi slash 4 and nu equals 0. SolidWorks assignment help.com. Figure 1. Top, conical indentation test and domains considered in the exercise. Bottom, indentation test results, loading and unloading. In this exercise, we are interested only in the linear elastic unloading part of the problem. 3. 0.1 Kinematically admissible displacement field. A kinematically admissible displacement field is a displacement field that satisfies the displacement boundary conditions on del's ID. For a rigid conical indenter, the displacement boundary is situated a. along the indenter material interface, along which SolidWorks assignment help.com, and b. at the boundary of the considered bulk domain, where ZID equals 0, in particular. The given displacement field satisfies these boundary condition, i.e. SolidWorks assignment help.com. Furthermore, the displacement field is continuous at R equals R, that is, the chosen displacement field psi is kinematically admissible. For a displacement field of the form psi equals Fz z R Ez, the non-zero strains A. Thus the strains and the strain invariance read, in domain 1. SolidWorks assignment help.com. In domain 2. Note that epsilon is continuous over the surface R equals R, while epsilon is not. The associated stress, ZZZR sigma equals 2G epsilon, is not continuous over R equals R, as it would be required if psi was the solution of ZR the elasticity problem, i.e. T, n equals R plus T, n equals minus R equals 0, sigma ZR equals 0. This shows that psi is not the solution of the problem, but just an approximation, appropriate to be used in an upper bound solution procedure. 0.2 Potential energy. We first need to evaluate the potential energy of the solution, which is conveniently evaluated from Clapeyron's formula. SolidWorks assignment help.com. In this displacement-driven test, phi psi equals 0, and the only contribution to the solution potential energy results from the displacement boundary condition. Next, we will address the potential energy associated with psi, in the same way as for the solution, phi psi equals 0 in this displacement-driven test, so that the potential energy can be entirely evaluated from the internal free energy in 1 and 2. SolidWorks assignment help.com. Thus, in domain 1, where 1 is in domain 2, SolidWorks assignment help.com. Hence, this potential energy is greater or equal than the solution potential energy. The previous inequality allows us to determine an upper bound for the indentation stiffness. SolidWorks assignment help.com. Remarks 3. If we use the solution, we obtain the sought upper bound of the indentation stiffness. 4. Using m equals e slash 1 minus nu 2, we obtain an upper bound for L slash R. For nu equals 0, we have SolidWorks assignment help.com. That is for h slash R equals 0, 1, L slash R less than or equal to 6.6, 8.2. It is also useful to note that L slash R infinity for nu equals 0.45457, which clearly shows some limitations of the solution. 5. It would now be appropriate to complement the upper bound approach with a lower bound solution. SolidWorks assignment help.com.